quantum attraction I will talk about today has nothing to do with people being attracted to each other because of some quantum phenomenon. Although it will enter in some living creature's life, which is the gecko sticking up glass walls. It's an incredible feature that the gecko has, and it's based upon a true attractive force which is of quantum mechanical origin. It's called the van der Waals force, and I will try and explain to you in brief where it comes from. Let me get back to the really simple basics of attractive forces. Everybody knows that if you take a positively charged particle and a negatively charged particle, they attract each other. Opposite charges attract. This is called the Coulomb force. Everyone knows that. The next level of sophistication is to take dipoles. A dipole is two charges of opposite sign held at some distance from each other. So you can imagine that if you have two dipoles, they will attract each other if they are oriented in the right direction. So in this case, there will be an attractive force between the positive and the negative here that is stronger than the attractive force between these ones because they're further away. So the two dipoles will like to click together along this axis. A real-life example of an electric dipole is water. Water is H2O. It's made of an oxygen atom and two hydrogen atoms. The thing that keeps the water molecule together is a covalent chemical bond where electrons are shared between the hydrogen and the oxygen. But in fact, there is a little bit more electron density on the oxygen side than there is on the hydrogen side. So the water is like a negative charge on the side of the oxygen and a positive charge on the side of the hydrogen. So the reason why water is liquid at room temperature is because water molecules like to be together. They attract each other through this force. And when you go below 0 degrees centigrade, it actually freezes and forms a solid because of these attractive forces between dipoles. Now let's go to yet the next level. Let's try and find out what is the force between neutral particles. And the simplest example of that is a hydrogen atom. A hydrogen atom is one positive charge, a proton, and the negative charge, an electron, orbiting around the proton. In fact, it doesn't quite orbit around the proton like the moon around the Earth, but it's spread out in a wave of probability around the proton. And this wave of probability is spherically symmetric. It's the same in every direction. Now let's imagine you take another hydrogen atom nearby, and you ask yourself, is there any force between these two hydrogen atoms? Well, you would be tempted to say that there isn't, because this atom is overall charge neutral. There's a positive and a negative charge canceling each other, and the same for this one. You would say, well, but this proton attracts to that electron. Yes, but it also repels equally strongly with this other proton. So if this was the end of the story, there would be no force between two neutral hydrogen atoms. In fact, things are a bit more subtle than that. This wave of probability of the electron around the proton has quantum fluctuations. So the actual position of the electron around the proton fluctuates in time. So you can well imagine that at some point in time, the first proton could have an electron cloud around it that is a little bit skewed towards the right. And if the same happens at the same time with the hydrogen on the right-hand side, then what you have is two dipoles, right? Because this is essentially like a dipole that is positive on the left and negative on the right, and the same on this one. So these two dipoles now attract each other. But these fluctuations of the electron cloud are random. So on average, the electron is around the middle. So there could be some time where these two hydrogen atoms attract each other, but then there could be another time when the cloud of the electron on the right-hand side, hydrogen, is skewed to the left, and so they actually repel. So on average, you would think they still don't have any force between each other. The interesting thing is that when you put them really close together, you get some form of correlation between the quantum fluctuations of the two electron charges. So in other words, if you calculate the average position, let's say along the x-axis, the horizontal axis of this electron, the average value is 0. And the same for this one. But if you calculate the product of the position of electron number 1 and the position of electron number 2, so x1 times x2, on average, is non-zero when the fluctuations are correlated, meaning that the fluctuation of one electron cloud essentially induces the fluctuation of the other electron clouds, so they go together. And when they do so, there is a net attractive force between these atoms that are otherwise charge neutral. This is a very important, very fundamental microscopic force of pure quantum mechanical origin. And the amazing thing is that there are large living creatures that use it. The geckos are capable of climbing on glass walls. They stick to the glass with an incredible force. And what they use is precisely a macroscopic version of this quantum mechanical force. And nowadays there are people who are trying to build robots that artificially exploit this force to climb, for example, on glass walls. You may have heard about bird navigation. There are some species of birds that in some seasons of the year migrate, for example, from north to south or from south to north to follow the seasons and the climate that they prefer. And for a long time, people have been wondering, how do these birds navigate? How do they know which way to fly? There is a very fascinating hypothesis in science, in biology, and in quantum mechanics nowadays, that certain types of birds use quantum effect to find what is the direction of the Earth's magnetic field going from north to south. So to understand how this works, I'm going to start from a very, very basic principle of physics and of quantum mechanics, which is the Pauli exclusion principle. Let's take, for example, a helium atom. A helium atom has two positive charges in the nucleus and two electrons orbiting around the nucleus. Now, you shouldn't think of these two electrons as moons orbiting around a planet. They are actually waves of probability around the nucleus. And so, in fact, they occupy the same space, the same cloud around the nucleus. And because of that, they need to obey what's called the Pauli exclusion principle, which tells that their magnetic dipole needs to be anti-aligned. Electrons not only have a negative charge, but they also have a magnetic moment. That's called a spin, although nothing is spinning in this case. And the Pauli exclusion principle tells you that the spins must be pointing in the opposite direction. Now let me clarify here that when I draw one spin pointing up and one spin pointing down, this is not a proper representation of the state that the electrons are in. These electrons are in what is called an entangled quantum state. Entanglement is a very special form of correlation that exists only in quantum mechanics, where two particles are correlated with each other, but they lose their individuality. So in this case, when I draw a spin pointing up and a spin pointing down, this is not the true entangled state. The true entangled state is one where the two spins are opposite to each other, but they don't have a state of their own. It's like taking two people and saying they have the opposite gender, but they don't have a gender of their own. Their gender is only defined in the correlation between each other, but not in the individual. This is in fact the kind of quantum state that two electrons sharing an orbit will have to be into. Now imagine you can separate these two electrons by some means. Then these electrons can move individually and flop around and precess and move. And so after some time, you may find yourself in a situation where the two electrons are now pointing parallel. Now, if that were the case, these two electrons could no longer go back together onto the helium atom. The Pauli exclusion principle excludes that. Okay? Now, the interesting thing is that there is a hypothesis, and I might stress, this is just a hypothesis, it's not easy to prove it, although there is some good evidence, that certain birds, in particular the European robins, use this quantum mechanical correlation to find the direction of the Earth's magnetic field. And the way it's presumed to work is this. The receptor is the eye of the bird. Imagine this is the eye of the bird. There is a retina in the eye of the bird. This retina contains some complicated molecules that are connected to the optical nerve of the bird. And these molecules may have some pairs of electrons that share the same orbit. Okay? So imagine these two electrons that are bound together and share the same orbit. Because of the Pauli exclusion principle, they have to have opposite spin, which I'm drawing like this, but remember this drawing is not the real thing because I cannot classically draw an entangled state. The next thing that happens is that if a quantum of light, a photon, hits the retina of the bird, the energy of that quantum of light can split the two electrons apart. So now I have these two electrons that are pointing in opposite directions. But now on Earth, we have a magnetic field. It's the Earth magnetic field. So I can draw it as an arrow like this. The magnetic field is normally indicated with the letter B. And in this magnetic field, these spins will start to precess. They will wobble around like a gyroscope. It's difficult to explain it in a drawing, and it is very likely to involve more spins than just these two ones, but the hypothesis is that depending on the orientation of the bird with respect to the Earth's magnetic field, these two spins may or may not remain in this quantum correlated, quantum entangled state. So now you have two possibilities. If they remain in the entangled state where they have the opposite spin, they can recombine together into their molecular orbital, and when they do so, they release back the original energy that was given by the photon. So in doing so, in recombining, they give out a stimulus to the optical nerve of the bird. Whereas if the orientation is wrong, these two spins end up parallel and they can no longer recombine, so the optical nerve of the bird does not receive the stimulus. The reason why this is so fascinating is not only because it is a possible quantum phenomenon that takes place in a living creature, in a bird, but also because it makes you think that there is an intelligent living creature that can see the quantum entanglement. I will keep talking about quantum entanglement over and over in this series of videos, but every time I will try to do so, I will struggle to visualize it for you because we cannot see the quantum entanglement. I cannot draw on the board a pair of entangled particles. Our eyes don't see it, but maybe the eyes of these birds can see it. You see, our eyes can only see light, photons of the colors of the rainbow, from red to violet. Whereas this hypothesis is that these birds can see more than we can see, and through the sensitivity to the quantum correlations between electrons in their retina, they can actually see with their eyes whether they're going west or they're going north.